going to talk about harmonics. What are they? Why do I care? How do I solve it? We're going to go through that. My name is Jeff Fell. I'm a senior application engineer for low voltage drives up in New Berlin, Wisconsin. Right now our high of today is about 55 degrees, so it's a little bit warmer here. It's nice weather. I like this. So let's dive into it. First, the topics we're going to cover today are harmonics. What are they? We're going to sort of talk about what causes harmonics. What kind of problems could they cause in your system? What to watch out for? How much is too much when it comes to harmonics? And then we're going to briefly cover what can I do to solve some of these problems with harmonics. How can I counteract these harmonic issues? The first thing we got to do is let's define harmonics. Harmonics are waveform distortions. There's a bunch of listings, under voltage, over voltage, voltage imbalances. Those are not harmonics. Harmonics is a distortion of the waveform, so let's first get that clear. When we look at power quality, there's a whole realm of different things you can look at power quality. So what are harmonics? Harmonics are non-sinusoidal currents or voltages that are present in any normal sinusoidal network. So they're always present. You're not going to get a perfect network where you don't have any kind of distortion. So we need to set some levels, and we'll do that down the road a little bit. What causes harmonics? Who's the generating cause of harmonics? Well, any nonlinear load causes harmonics. Examples of those are non-incandescent lighting, computers, copying machine, battery chargers. Anything that takes AC power in, converts it to DC is a nonlinear load. So number one, the biggest probably loading of that is what these guys, right? Drives, VFDs, right? So even these lights that are above our head are nonlinear loading. They're causing harmonics in the system. Looking at this, a couple things that we sort of hit on already, but line transients or non-repetitive events are not harmonics. So if you got a transient running down your line, that is not a harmonic. That's a power event that occurred, not a harmonic event. Okay. Harmonics are basically a mathematic qualification or analysis of the system to determine what's there. Okay, so we're going to use math, and we'll see that in a little bit more. Harmonics are both present in the current and voltage distortion. So you can have both, and they sort of go hand in hand, and we'll see that in a little bit in some of the slides I have. All right, nonlinear currents generated by nonlinear voltages through electrical network. So basically, if we have current distortions, those in turn cause voltage distortion. So higher current distortions you have, in turn, the higher voltage distortions. Okay, they sort of go hand in hand, and we'll see that coming up. So if we look at this, this is a nice sinusoidal, perfect sinusoidal waveform. What I would expect, this is a perfect example of a linear load, right? It wouldn't be these lights above our head. Maybe an incandescent light bulb, right? No harmonics on the system. This is a non-linear load, right? This is what a VFD, if I put a current clamp on that VFD and look at the currents going into that drive, this is what I'm going to see, these two bunny ears. I like to call them bunny ears, or the two camel humps. And basically that's the conduction of the drive. Interesting thing, if you ever look at this, this drive's pretty lightly loaded. Well, how do I know that? Depending on how far the center peak dips down tells you how heavily loaded the VFD is. So the more load on the VFD, you'll see that trough down more. So if we look at this and we lay this sinusoidal current or current form on top of the nonlinear form, the blue line is actually the harmonic content within those two waveforms. But if we look at this, right, as this goes up on this peak, we actually push this blue waveform down, right? And you can see it's sort of matching itself. It looks kind of crazy, but that's what we're looking at. That's the distortion, the current distortion that the harmonics are causing in the system. Look at the green line. The red line is our fundamental current for the drive. That is about 70 amps. If I square that, what does that come up to be? 4,900, yeah. If I take the distorted portion, this guy here, roughly, and say that's about 20 amps on the level, And I got it on my slide, so we'll call it 20 amps. If we square that, that's what? 400. If we add the two together, 5,300. I know it's hard math. I stumbled. I had to calculate it ahead of time. And then we take the square root of that. It's about 72.8 amps. So that's the total current the system would have to supply. Even though the fundamental's only 70 amps, the total current the system or the transformer would have to supply to the system is basically 72 amps. 20 amps of harmonic currents, 70 amps of fundamental currents. So a total of 72 amps. So if we looked at this and did the mathematic on it, we got a current distortion, or a THD, of 28%. If we look at current distortion, and everybody likes to talk current distortion, it's real easy to remember something. If I increase the fundamental, my current distortion will go down, right? It's a ratio that we're working with. So if you need to combat harmonics in your system, there's a couple things you can do. One, reduce the harmonics, right? What if you can't reduce the harmonics? Can you put more loading? What kind of loading would we want to put on that transformer? Linear loading, right? We don't want to put more nonlinear loading because we're creating more harmonics potentially. We want to increase, typically we want to put linear loading on that transformer, bring the fundamental currents higher in the system to offset how much distortion we're having in our harmonic distortion. So what's the root cause with other equipment? Typically current distortions create voltage distortions. So if we look at this, I got a 1.5 MVA transformer. I got a 75 horsepower drive. Here is my voltage waveform. And if I look here, here's my current waveform for that VFD. And you can see I'm pulling a significant amount. But if I come down here and do the analysis of how much harmonics are in the system on this transformer, this is a pretty heavy-sized transformer for a 75 horsepower drive, you can see I got a current distortion of 37%, and I got a 0.9% voltage distortion. Pretty minimum on the voltage distortion. So if I take that same 75 horsepower drive and move it over to a 75 kVA transformer, pretty small guy now, you can see what happens to the voltage. It's not a very nice voltage waveform anymore, right? We got some flat topping going on here. So you can see what happens. And with voltage and current distortions and harmonics, impedance of the transformer comes into play. If we put a larger transformer compared to a smaller transformer, a larger transformer has more impedance or less impedance? More impedance, right? So the higher we have impedance, the better we look or get better voltage ratios out of it. And we'll see where that comes into play with IEEE 519. But you can see also what happened. My current distortion actually went down compared to this slide of 37%. But my voltage distortion went up because I have less impedance in my system now. Okay, that's also with your cabling that you put in your system as well. So what problems why do we care about these harmonics? What problems do they cause? Harmonics can cause basically you to increase the overall system, right? That transformer has to supply the fundamental currents, also has to supply the harmonic currents within your system. If you want to think of the harmonics currents as waste in your system, that's what it has to supply. So back when we were doing that example of that 70 amp drive, I had to size that transformer for 72 amps because I had basically, we'll call it 3 amps because we'll just call it 3 amps. I had to put an extra 3 amps in that transformer just to supply these harmonic currents that don't do any work for me. So the same thing goes true. If I don't take care of the harmonics, I'm going to have to size my equipment larger. I'm going to have to size my conductors larger. I'm going to have to size my fusing larger. This can also cause component heating if you don't do it correctly, right? I can wear out that transformer. I can heat it up too much. Very typical in wastewater, right? These pole transformers. They had motors across the line. Throw a VFD in there. Well, Now that transformer has to supply that motor current, right? Before it was no problem with just the motor. Now you put a VFD in there. Now I got to supply the fundamental currents, and I got to provide the harmonic content currents as well. Well, now that transformer is not big enough. Now it starts to overheat, eventually fail. So you got to be aware of these. One thing that it can do, and most people, this is their driving factor, is your power factor. Utility will fine you if you provide a bad power factor to your neighbor. Sometimes I heard a guy where he was getting fined 60 cents per kilowatt because he had a bad power factor. That's what the utility was charging him, pretty much for like a 500 horsepower drive that he had on there. So you can imagine what his bill was. So he was looking at a way to fix his harmonics in his system. You can also have equipment malfunction. For the VFDs, we create harmonics. We really don't care. We'll create all the harmonics all day. But you could have problems with your zero crossing, or if there's too much voltage distortion, you could cause flat topping with that small transformer where we saw the top of the waveform chopped off because of harmonics. You can also get a resonance in your power system if you got power factor correction caps. You can make them to start to oscillate and cause overvoltages, spikes. Other things can occur in your system. So how much is too much? There's a governing body or a suggestion from IEEE 519 that gives recommended requirements for harmonic control in electrical power systems. So they are the ones that everybody, I'm sure you heard 519, IEEE 519 is the standard we use in the industry. So if I pull this out of the standard from 519, this is the 1992 standard. It hasn't changed. These two tables. Let's first look at the voltage limits. IEEE they're not worried about the current distortion in the system. Everybody uses current, but it's really the voltage distortion that they're worried about. They're trying to make sure that you're not going to screw up your neighbor's power. But if we look at this, there's not just one level. There's special application. Hospitals and airports got a 3% voltage distortion. You got general systems got a 5%, and dedicated system gets a 10%. Well, why are hospitals and airports, why do they get this special requirement? Why? Communications, people's lives are online, right? I mean, I want to make sure if I'm landing in an airport that has a 10% voltage distortion and communication equipment can go out, I don't want to land there. I want to go find that 3% distortion somewhere. More reliable systems. Yeah, people's lives are online, so we want to keep those in check. General system, this building here. But if I have a dedicated transformer where it's just VFDs and VFDs alone and it's dedicated for that, I can go up to a 10% voltage distortion. VFDs, we create them all day. We don't care. Go ahead, give us 10%. We can still operate on that. It's nothing for us. So one thing you got to remember with IEEE 519, there's just not this flat, this is what you need to meet. There's all these different caveats that you got to be aware of. And if we go down here, we see this guy, ISC versus load. ISC. Well, what is ISC? Well, ISC is the short circuit capability of your transformer. So what does that mean? Well, if you went up to that transformer, snuck up on it, walk up, you got this copper bar. And if you threw that copper bar onto that transformer, well, make sure you got your scope set up and triggered and ready to go, and then run. And measure the short circuit capability current of that transformer. That would be your ISC. Tells it how much current can that transformer put out. So depending on the size of your transformer, you will meet or fall in different levels of acceptable TDD levels. Well, what's this TDD? I'm used to hearing THD, total harmonic distortion, right? What's this TDD? Well, we'll see in a second what TDD is, but that's what we use. In this area here, they're talking about current distortion, or THD. Well, what is TDD? Well, if we look at this, this is your THD here. Here. I was looking at voltage. Your I fundamental. So here's your fundamental currents coming up. Here's your current distortion. your I or your current THD, and then here is your I harm or your TDD. But you can see as loading increases, our harmonics come down, right? So your TDD is here at 100% load or 100% power requirement for your system. Well, why would I want to take it there? Wouldn't I want to take it back here where the harmonic content's the worst? Well, no, I don't want to do that, and the reason for that is what IEEE is worried about is voltage distortion. So if we take that same number and let's put voltage out here, this is where your this is voltage distortion as well, but you can see the worst case for voltage distortion is at 100% load. So the TDD is what IEEE says you need to look at. You need to look at worst case scenario for your facility and what's your voltage distortion going to be at that point of time. So basically the goal of IEEE 519 is thou shalt not mess up your neighbor's line voltage. We don't want distorted waveforms going to the next one. So in IEEE 519 there's also PCC, and that defines the point of common coupling. The problem with this is it can be very unclear. People read this as different ways. People try to take IEEE spec and apply it to a drive. I want IEEE 519 at the drive terminals. I want IEEE 519 on my 1 horsepower drive. Okay, how much money you got? It's going to be very pricey. So they try to apply a standard or a spec across the board and solve every problem. But really the way the standard was defined was at the PCC, point of common coupling. So if we look at this, where's that PCC? Well, it's basically where the utility system ends and the customer system picks up is sort of your point of common coupling. So if we look at this, it would be here, it'd be here, it'd be here before this transformer going into this facility. Basically what IEEE 519 is trying to do is keep the voltage distortion that this guy's going to see from this facility basically to a minimum. That he's not going to flat top the waveforms when it gets to this guy and he's going to have problems. So when this factory fires up, all of a sudden this guy, nothing's working. His radios aren't working, telephone lines aren't working. He's shut down. You just shut down your neighbor. That's what they're trying to avoid. So this is the basic AC drive. We got dial front end rectification, DC bus in the middle. So we take that AC in, convert it to DC, fill our capacitor bank, and then when you tell us to modulate that motor, run the motor, we start firing the IGBTs on the output and supply power to that motor. So looking at this, there's things missing. This could be a small drive. There's no kind of reactance. Usually in a VFD, there's some kind of reactance in there. Most of the micro drives won't have reactance in there. We'll talk about why I'm talking about reactance here. Solutions that I can use for a VFD is one, I can add reactance to the system. I can add chokes. They can be line chokes, AC line chokes, or DC link chokes. We have a patented swinging choke in one of our products we'll talk about. Or I could put a drive isolation transformer in front of it. Would help. I'm adding some impedance to the system that's going to help mitigate some of that harmonics, right? We talked about that larger transformer, right? When we got that bigger transformer, what happened? The impedance went up, right? Same idea, we're adding impedance to the system. We could also look at passive or harmonic trap filters. We can look at those, and we'll talk about a couple manufacturers. A couple are here that sell things. There's also a solution with a pulse, high pulse count rectification. So 12 pulse, 18, 24, and 36 pulse. The last thing you can do, and this is out on the show floor, I was just looking at it, is basically the standalone active harmonic filter, or the other thing that we offer as a drive is our ultra-low harmonic drive where you got an active front end in it. So what's the simplest? I don't got a lot of money, I want to fix my harmonics. Well, the simplest, least expensive technique is to add reactance to the system. One thing to remember is it might be included in the drive itself. The drive might have reactance already built in, DC link choke or AC line choke. Often meets the harmonic needs provided for small loads in the system. May be implemented, like I said, with an AC or a DC link choke. Basically, what the AC choke provides is some impedance for the front end and gives you some impedance protection. But a DC line reactor actually provides better voltage regulation, is what it does. Both are similar in the harmonic benefits. AC choke is pretty much the same as a DC choke. There's really no difference between the two. The one thing that we do have is our swinging choke, and we'll talk about him. The benefit to him is when he's lightly loaded, you still get a higher harmonic mitigation than you would from a standard DC choke. So where would a line reactor fit in our little drive picture? Here's our diodes, here's our capacitor bank, here's our IGBTs. AC line choke would sit on the front end. It could be an external device. It could be built into the drive. Our 850s have them built in. We got a 3% line reactor basically. In a DC link form, it sits right between the capacitor banks, typically in the plus and minus leg of the DC bus. Basically, like I said, they're equal in performance. It doesn't really matter where they're placed in the system. That's a standard question. And if a drive has a reactance or some reactance in it, typically you're going to be anywhere from 46% current distortion down to about 28%. It all depends. A drive with no reactance whatsoever, you're going to be up probably about 72, 78% current distortion. Now, typically those are small drives, right? So everything's relative, right? If I put in, say I got that 1.5 MVA transformer and I put a 5 horsepower drive in there, do I need to care about harmonics? No, it's peanuts compared to the overall size of that transformer. Plus our levels go up, right, in that IEEE table, or I should say they go down. What if I put 100 5 horsepowers in there with no DC link chokes? I might want to start looking at that because now I just put 500 horsepower with a current distortion of 70-some% in my system. I better start looking at my numbers and seeing what that's doing to my overall picture and where I'm at. Start doing some looking at the system. Here's an example of a DC link choke, just an idea of what they look like. Here's a line reactor. Line reactors, MTE, is where typically if you call in and need a line reactor, that's where I'm going to tell you to give them a call. They'll be able to help you out. So if I look at this, well, how much is, well, let me put a whole bunch of reactants in my system. Is that going to gain me anything? Well, if we look at this, here's our current distortion level. So we got 100% current distortion all the way down. But you can see as I add reactants to my system, and these different lines are our short circuit capabilities of our transformer. So that's when I snuck up on that transformer and threw that copper bar at it and then quick ran away because that thing's about to just blow up. That's what we're looking at. So if you got a real small transformer, that would be this guy, or compared to a real large one, you can see the benefits. You can see about 3% you gain some, but when you go to 5%, you're not gaining much. And in anything past that, you're sort of negating the process because now as you add reactants into the system, what also happens on that reactor? What's the side effect of that? Anyone? Voltage drop, yeah, thank you. Voltage drop. So what happens is you get more and more voltage drops, so now you might be hurting yourself because you can't get enough voltage to your motor. So now you're voltage starving your motor. So there's other things that occur, so you got to be careful. So if you look at we got a patented swinging choke. The difference between this is the design of it. Basically it's equivalent to a 5% line reactor is what you get. And the benefit of this is when you're running lightly loaded, typically on your DC link chokes, you know, they got a 3% impedance or a 5% impedance. But as soon as you back off from full power, the impedance of that system drops pretty drastically on a normal choke. So our patented swinging choke with the air gap, basically you can see what happens to a fixed 3% choke, the red line, and then you can see what happens to ours, that we stay pretty much up there. The disadvantages for at least the transformer, maybe I'll hit those. It's pretty expensive. Size, right? If I put in reactants and stuff into my cabinets, I got to find room for that. Also need to worry about the heat of that. Adds heat. Voltage drops at full power. We need to worry about that. But it's a cheap and easy solution. So if you're just right on that edge, maybe adding some reactants would help you. 6-pulse filters. There's a couple out there. There's a passive or a harmonic trap filter or a passive notch filter. The benefit of using these is typically I can size those filters to basically feed multiple VFDs. So if we go back to that scenario I said with the 5 horsepowers, and I put 100 of them, I can maybe break them up into section and put one filter for maybe a couple of those VFDs and compensate for bad current distortions at those points. Typically with these kind of filters you get it anywhere about 10 to 14 THD is what you're looking at, current distortion numbers. Performance can be reduced by a line imbalance, a voltage imbalance. One leg is lower than others, right? No, not out in our world. Everything's perfect, right? All nicely even, perfectly balanced. Some things that you got to be aware of is your power factor might go leading as well with these filters, so you got to be worried about that. Watch that. Be careful of that. Here's a couple of the trap filter types. Maris has one. MTE and also TCI. A harmonic trap filter, same thing, I can use it to feed multiple VFDs. Pretty much the same things that you got to watch out for. If we looked at a tuned trap filter, it's basically tuned for that system and it's going to filter out some harmonics from the sort of utility system itself. You got reactors and capacitors, and they're selected to shunt the harmonic currents to ground, basically, is what they're doing. They're filtering them to ground. TCI has one. You can see there's a lot more components in here compared to that last filter that we were looking at. It can be used to improve the harmonics, not just what the VFD is causing. It works across no matter what the loading on the VFD is. The size, you might want to consider. It's pretty sized, and can be expensive too as well, but it's a solution. A passive filter, a broadband filter, Maris has one and MTE has one, and what that is it shunts, it's an auto transformer and it's shunt capacitor network is what's built into these. So that's sort of the schematic layout of that filter. Benefits: reduces the harmonic currents. Will not improve the system currents, so it won't do anything for the overall system. Reduces the input line currents and available in all horsepowers and all sizes. It's more expensive than a line reactor isolation transformer. Typically any filter solution, it's going to be more pricey than the rest of them. Typically this is the area I like to go to, and this is where most people go to. They go to a pulse solution. High pulse rectification solution. If we look at this is our 6-pulse drive. It's just a reactor. Maybe there's a line reactor or a DC link choke in there. Our next solution would be a 12-pulse rectification. You can see we got a transformer in here. We got some additional dial rectification going on. And you can see what the voltage waveform, the current waveform looks like with a 12-pulse solution. We go to an 18-pulse, very common out in the industry. You can see I gain a larger transformer, more diode rectification. You can see we're getting close to like a sinusoidal current draw back to a linear loading or a linear current draw. And then we could get to our ultra-low regenerative driver active front end, where you basically take you got a AC to DC conversion with an active front end. So I got a full-blown IGBTs in the front end, and I can gate them on wherever I need to. Okay, you can see pretty much the same current draw as what 18-pulse would offer to a system. The benefits from going to this guy, you're getting more hardware. That cabinet's getting larger. Okay, now I got a transformer I got to worry about. I got to size the enclosure big enough for that transformer. Also have more diodes in there. It's more complex. For a guy coming in to troubleshoot that, there's more components there, more things to go wrong. If I look at this guy, bigger transformer, more hardware. The benefit to going to the ultra-low harmonic drive is I don't need a transformer. I don't need those extra bridges there. The drive does that. Basically, it's all built into one packaging. So performance goes up as you go across these. There's configurations out there, 12 and 18. That's typically where the low voltage drives stop. There's also 24 and 36 used in the medium voltage side. So basically requires a phase shifting transformer. Additional bridges are needed. You can see here's your levels for current distortion. So you can see a 12 pulse gets you down to about 8%, 18 pulse down to about 5, we'll call it. 24 really gets you down there, and then 36, medium voltage, different world. Performance can be significantly reduced by a line impedance. Well, you got a phase shifting transformer there. If your voltage drops, it sort of screws up the conduction a little bit and the way the diodes are going to actually provide power to that system. It's an excellent choice if a transformer, a step-down transformer, is already required. So if you already need an isolation transformer, then it's not that bad because you already need to buy that component anyway. So now all you need to buy is those diodes and the rest of the hardware for it. Most often the case with medium voltage drives, you need some kind of transformer there, so it's an excellent solution for that. You can see different layouts. There's a parallel bridge design. There's a series bridge design. We got this, we call it a poor man's 12 pulse. We'll sort of look at that. And basically what that is where you're just using 2 VFDs and making a poor man 12 pulse. And the way the 12 pulse poor man works is basically we got a Y to delta transformer that causes a phase shift in our power system. And with that, we just load up 2 VFDs, and you can see here's the typical sort of the current distortions as loading goes up. Basically, you can see where we're at with the normal, say, just a simple 6-pulse drive. But if I add one on a second line, you can see what happens to the 12 pulse or the poor man 12 pulse. The conduction of this drive is offset by this drive, and you basically get your levels back down to here. And here's just a normal true 12 pulse of what your THD numbers would look like. But the one thing you got to remember is if you shut him off, this goes back up to this level. Is that going to be a problem? Well, it depends on your system. Now you just dropped your fundamental currents right down, so everything's at a lower level. So where's your voltage distortion? Ultra-low harmonic or active front-end drive with the isolation transformer. This is what we sell at ABB. If you go down and look at the ultra-low harmonic drives down there or regen drives, our drive has a LCL filter in the front end. And that's to clean up the high frequency, the PWM frequency, the high switching frequency before it goes back to, or where we conduct on a utility line for the regen, it's to clean it up when we regen back to utility. So if we look at this, this is what the currents look like near sinusoidal. We will meet IEEE 519 at the drive terminals. So if a customer calls in and is looking for a drive that needs to meet IEEE at the drive terminals, because that's how his consultant wrote a spec or that's what he wants to do, I'll be happy to provide a drive, and here's a part number. If we look at current distortions, basically we meet it. Here's our harmonic numbers showing you a ratio there. The one thing is our voltage distortion is always less than 5%. And the one thing nice about the ultra-low harmonic drive in the regen drive is we have out-of-the-box unity power factor. So we don't do anything to the power factor, and we can actually make the power factor go leading or lagging. It's actually adjustable inside the drive. Here's the 2 flavors. There's a wall mount that goes from a 10 horsepower to 125 horsepower. And then we also have a cabinet drive that goes from a 75 horsepower up to a 2,800 horsepower is what it goes to. Medium voltage also has an active front-end drive. They can go from 300 horsepower all the way up to 3,000 horsepower medium voltage. A couple of nice things is the unity power factor. The biggest benefit is hardware. Definitely smaller physical size. No dedicated transformer needed. Lower losses. Overall efficiency is better. Reduce size. We can also reduce the size if a backup generator is used. We're not going to distort the voltage waveform. We got unity power factor. Typically for VFDs, you need to size your generator about 2 times whatever your VFD load is. If you got an ultra-low harmonic drive, you can go about 1.5 times the size for generator power. You can reduce it because that generator doesn't need to supply that harmonic current anymore. We're very clean power, what we're conducting. It's more costly over a reactor in a passive sine filter. Large footprint in the smaller sizes, so we have, if you guys are familiar with the frame, our 5 frame is the smallest ultra-low harmonic drive, even though it's 10 horsepower, but that's the physical side because you got 2 VFDs in there. So as we go up, you can see what happens. No mitigation, you're about 72%. And as you do things, what you bring those current distortion numbers down to. One thing to remember is it's a ratio, right? So our harmonic content divided by our fundamentals. So you remember, if you want to offset some harmonics, increase your fundamental will help you. So thank you.